today I want us to progress on digital filters. We are going to look at digital filter characterization. Basically, what we started yesterday in the introduction, just going a bit deeper. We started looking maybe even what we looked at yesterday. What a digital filter is, the way it can be described, why we do digital filtering. I think by now we know that. We know that most of our communication systems are digital, and they are more designed to carry data. So in that case, when we want to carry analog signals like voice or video, we have to actually digitize it. You have to convert it to digital and then use the same systems you're using for data. So, and of course, they have more advantages, as we said yesterday. And they are not affected by things like components overheating, which would affect analog filters. So we said that a filter is an LTI system, of course. So it can be characterized by the impulse response, the system function, and now we have seen also by difference equations. So in this lesson, of course, we are going to look at these relationships. I think we started looking at that yesterday. And what we are saying is that, I think we talked about yesterday still, is that a causal discrete causal LTI system can be fully described by or characterized by a linear constant coefficient difference equation. Yeah. So we are going to look mainly at low pass design of low pass filter. It's normally the easiest filter to design. And when you're designing digital filters, normally you can either start with a low pass filter and then through some methods you can convert it into a high pass filter, or you can design it in the continuous time domain, the analog domain, what we are used to, especially because there's a lot of design has been done. A lot of what do I say? There's a lot of characterization of filters, different type of filters, Chebyshev, depending on whether they have a ripple at the stop band and the pass band. They have a steep transition or not. So it is easy to design in the analog domain and then convert to a digital filter. Yeah, and that's what we are saying. At the end of the day, that's how we design IIR filters. We start with analog, and then through various methods, which we are going to look at the end of this filter topic, you can convert into digital filters. But when we are doing FIR filters and we start off from low pass, we can convert to high pass through what we call spectral reversal. And actually that spectral reversal is done very easily from the impulse response point of view, which is its time domain, it just involves changing I think the best way is to put it is multiplying by -1 every other sample of the, of course, which will be the coefficient. When whenever you talk of a response, we call them samples, but they also, for FIR, they also correspond to the coefficients. So it will actually what it will involve is like if your filter is represented by, let's say, 1, 2, 1, I mean the HN of that filter, the HN of that filter is, let's say, 1, 2, -1, 3, 2. So it has got 5 coefficients. But you're doing the filters and I call them coefficients, but normally, of course, since it's a response, we normally call them samples. So if you have this HN, when you talk of spectral reversal, it means now your HN will change into every other, inverting every other coefficient. So this will become 1 -2 -1 -3 2. So your new filter would have this impulse response. So it will simply become a high pass filter. That's one of the ways of, that's what we are talking about, spectral reversal. And of course, it comes from the shift theorem of the Fourier transform. That is actually the frequency shift theorem of the Fourier transform, where in the in the frequency domain, a shift, if you have a shift of A, if your frequency shifts by A, if there's a shift of A in the frequency domain, it is simply, in the time domain, it's simply multiplying by E to the minus J W, J W A. I think it should just be multiplying by N W A. Yeah, I hope this is it, because eventually what happens when you convert this into and of course that A is simply should be N over 2 samples. I mean, I think that's what I checked in there. Going to say, but anyway, I cannot fully remember. But if you convert that, if you actually work it out, you're going to find that I think it's either WAN or something, or JNA. whether W is there or N. But if you convert this, if you use the Euler's formula to convert this, actually where it comes from is if you use the Euler's formula, I think let me not write it because I can't remember it fully. If you convert from if you use Euler's formula and convert it into sine and cosine, what happens? Of course, the sine terms become sine n pi, j sine n pi, and the other one becomes cos n pi plus j sine n pi. If you choose your A, that shift to be n over 2. Yeah. So if you choose n to be, I mean that is the limit. I mean the n in the DFT. Yeah, the capital N. If you change to n over 2, if your shift is n over 2, of course, what you're going to get, you end up with this, and this term becomes 0. And so n, when you change the n, when the n is increasing, it will be going from positive to negative. Yeah, as you increase n, cos pi, cos 2 pi, I think it will be going from I think I was wrong. That it will be this squared. Sorry, it will be squared. So cos n pi, I think it's -1. So when you square, I think this one can only be explained if I actually do it from this. Okay. But actually, you can check that. You can check that. I think this is where I was wrong. It is actually -1 to the n. So it's cos pi to the n, hn. Anyway, you can check through this. Alternatively, you can go through it again. I think I'm trying to remember the but actually that is how you end up getting the spectral. Yeah. So, I think it's explained. Oh, it's even explained here. Why am I explaining something? Oh, it's already here. Oh, apologies. It's here. I'm not even seeing it. It's here. So this shift is simply the same as multiplying with this. This is what I was looking for. J2 pi NA. So I think from here you can easily be able, if you convert this into sines, then you can see why actually Hn ends up being. If this was Hn, it will end up being having every other term inverted. Sorry about that. I was trying to explain something which is already here. I was not even seeing it. So you can try to work that out. And I think the important thing is to know that how you get the spectral reversal, and of course, spectral reversal can be used to create a high pass from low pass. I think that's what we have talked about. I think the difference equation is what we talked about yesterday. I think we already have looked at this. I think now you're familiar with both forms. Of course, one form is where you express this summation, bingo to this summation, and the other case is where you express y of n as a difference of these two summations. Yeah, and we talked about this. So any filter can be achieved by varying the filter coefficients and the number of delay elements. The number of delay elements will depend on what you want to achieve. Yeah, as the number of the elements increases, you go closer to the ideal filter, which is a boxcar. Is the one that completely completely removes the undesired frequency immediately. I mean, without without any transition, so to speak. Yeah, that should be the ideal filter. So by increasing the number of elements, you go as close as possible to the ideal filter. These samples, of course, are feedback. I think we talked about that yesterday. If n is 0, the filter is not recursive, or if IR, if n is equal to or greater than 1, the filter is IIR. EK coefficients are feed forward, or EK, I think we talked about this yesterday, unless somebody would like me to talk about them again. So this is the characterization. If you want to build a filter, you're going to come from the difference equations and then draw your block diagram. This one helps you in the implementation. And this, I'm just trying to prove a point, but in most cases, you don't draw the block diagrams like this. You have your summing only having 2 inputs and 1 output. So usually they will be like that with the 2 inputs and 1 output. Then this output goes here. Then you have this input and that output. And eventually you join here. So I was trying to prove a point here, but when you come to drawing the block diagrams, this is how we draw them. And such a diagram, of course, is what we call a direct form, a block diagram. So that generally the diagram will look like this, and this is a general diagram for x and x of n minus m. Yeah. This is a block diagram for IIR. Yeah. This is for FIR. The IIR, this will be one of the forms of IIR. Yeah, again, this is direct. This one we call it direct form 1. So we are going to see different direct form 1s, and later we are going to see for IIR you have direct form 1 and direct form 2. For FIR, we have also different structures. We have, of course, direct form 1, which I think I better do it again, maybe for, I think I'll do it somewhere else. Let's say just for see. That's a one delay unit. Decided to do the way we expect to do it. And this will be, oh, there should be coefficients here. It's a multiplier. You can either do it this way, or in some cases it will be drawn like the symbol or like over diode. Or sometimes it's just an arrow with a number, with the multiplier, with the coefficient. Yeah. So it could be in this form. Here I have drawn it in this form. Let me stick to that form. Yeah. And up to the last one. sorry, like this. So this will be your yn. Oh, even this outfield is not clear, so this will be your in. Your yn. Yeah. So it will be something like this. And this is, of course, we said that the order of the filter is the number of delay units. So when you have 2 delay units, that's a second order filter. So you can have this is what we would call direct form, and a direct form is directed from the equation. So I think later you can look at when you create different forms, of course, also you have to reorganize your equation. So this one is called direct form because it corresponds directly to the difference equation. We are going to see later that you can actually reorganize your difference equation and you have a different form. I think we talked about the moving average filter yesterday, and I think I've just reproduced the same here. Basically, this is just a repetition of yesterday. What's a digital filter? I think this is just what we said yesterday, so I don't think I need to repeat this again. Unless anybody has a question, I think we went through that. We don't have to. I think we went through this. So unless anybody has an issue, we don't have to go through it again. The transfer function of a digital filter is given by that, and if it is FIR, yeah, it doesn't have the A terms. Yeah. And I think yesterday we looked, okay, this is a different example. We can look at this example. It's a different example. So here you're given a difference equation. We did yesterday, but this is just a different example. So you have y of n is equal to 2y into n minus 1 or 3x of n. So the transfer function is just h of z is y of z over x of z. You take the z transform of both sides, so that becomes zy of n, and this z of this and the z of this. Then, of course, so y of z is simply 2y of z, z to the minus 1. Whenever you have this delay, you have this z to the minus 1, and this is 3x of z. So y of z minus 2y of z, z to the minus 1 is equal to 3x of z. Therefore, y of z is equal to 3x. Y of z over x of z is simply 2. Bring x of z this side, and bring 1 minus 2 of z to the minus 1. This side, you get that. Multiply the denominator and the numerator with z, so you get 3z into z minus 2. Yeah, that's what you get. Let's see what you want to do that. You can also now do the opposite, difference equation from the transfer function. This is an interesting one. So this is your transfer function, h of z is 5z plus 2 divided by z squared, I mean z to the power of 2 plus 3z plus 2. So, of course, you know, when you deal with the difference equations, you don't have future terms. And of course, that's what something like z squared or even z means. It means you actually have future samples. So you'd have to divide by 2 so that you don't have any future samples. So what you end up getting is delayed samples. Yeah. So you divide the denominator and the numerator by z to the power of 2. So this will become 5z to the power of 1. Yeah, of course, you do it with the highest power. If you do it to the highest power, of course, that highest power will not have a z. Yeah. And the others will have z to a negative power, which will symbolize in the difference equation that would be a delay. So I think it is clear why we have to divide by the highest power. So if you do that, you are going to get 5. And of course, when you divide numerator and denominator, we know that that does not change the value of hz. Yeah. So this becomes 5z to the power of minus 1 plus 2z to the power of minus 2 divided by 1 plus z to the power z, times z to the power of minus 1 plus 2z to the power of minus 2. Yeah. And that hz is yz over xz. So we just replace hz with yz over xz. So of course that becomes x of z times 5 to the z, 5 times z to the minus 1 plus 2 z to the minus 2 and y. So you end up having this as your difference equation. You can reorganize it so what you have yn is the current sample of yn is given by these past samples of x of n and these past samples of y of n. So I think that is clear. Actually, you don't have to do this. Yeah, it was straightforward. I was thinking we normally use this when you're trying to get h of n, but we are not trying to get h of n. We are just trying to get y of n from y of z. So I think there is no question up to there. We can proceed. Any questions? This is the example we did yesterday. I think the problem we had yesterday, I had corrected it here. Yeah, the same example we looked at yesterday, and somebody pointed out there was to be a minus 1. And we corrected, but I had actually corrected it myself before in this newer document. Yeah. So here you're given y of n is equal to 0.5, y of n minus 1 plus x of n. And you are asked, I'm just going to do the same example, just in case anybody did not get it yesterday, you have another opportunity. So you are given y of n as that. It's a difference equation, and then you have been asked to look for the frequency response, magnitude response, and phase response. Yeah. So you apply the z transform to both sides of the above equation, and of course you are going to get y of z into, yeah, of course, we just reorganized. We apply the y of z and x of z, and then of course reorganize, and you're going to get y of z into 1 minus 0.5. Z to the minus 1 is equal to x of z. And y of z minus this, so which can be written as this, yeah? This can be rewritten, what am I saying? Looks like I was going the opposite. It should have been, yeah, actually from here, you don't have to, I don't know why I was even having this. So this can be written as h of z is y of z over x of z, which is that. And then we let, to get the frequency response, we have to let z is equal to e to the j omega. So h of omega is 1 over 1 plus 1 over 1 plus 0.5. Where did I get the plus? This is a mistake again, eh? Where did I get the plus from here? This is minus. Sometimes I do this in such a hurry, I make this again as a mistake, but I think I corrected it here. Yeah. So is that, and then of course we get that. We looked at it yesterday, so so that gives us a frequency response. Yeah. Magnitude response. We also did that. So of course it's simply the square root of x squared plus y squared if you have x plus jy. So you have to reorganize it to be in this form, and that's why you have here 1 minus 0.5 plus omega plus j sin omega. I hope my signs are okay here, but what is important is the concept. So you can get your magnitude, and then of course you can get this response, which is simply, in this case, will be the angle of the denominator, a numerator minus the angle of the denominator. So that's it. So I hope everybody is okay with what we have looked at. And I think if you're not okay, it will become clearer as we do the examples, or as we look at more of this. So this is just a review of what we have already covered. Filters are used to achieve frequency selectivity of the spectrum. This could be to remove high frequency noise from low frequency signal. Yeah, this is a normal example, quite a common example. You have only the signal and you have some high frequency noise. We are generally just talking about out of band noise. Yeah, out of band noise, you can easily remove it. So for the filters, we are saying the continuous signal is converted to digital by we have talked about that. Samples are then processed by a DSP, or I know I put a microcontroller, I should just microprocessor. FIR advantages. Yeah, since we are doing FIR design, we are talking about the advantage of FIR over IIR. Requires no feedback. That's making the implementation simpler when you have no feedback. They are inherently stable. The moment you have feedback, issues of stability occur. It is easy to design to be linear phase by making the coefficient sequence symmetric. You want it to be linear phase. You don't want distortion in the signal. Yeah. So, and it's very easy to do it, as we are going to see with FIR, so long as you make coefficient sequence symmetric. So what do we mean by sequence symmetric? Would mean if you have coefficients like, let's say 1.5, 0.3, 0.5, 1. That's what we call coefficient sequence symmetric. Yeah. So if you have this, then you end up getting a linear phase FIR filter. Yeah. If it's a linear phase, it means its coefficients will actually have this kind of symmetry. Yeah. This is just when you have 5 coefficients, because this would mean this is what does that mean when you have 5 coefficients? It's order 4. That should be, the order is 4. Yeah. So the main disadvantage is that there is more computation. And I think we saw yesterday with a simple filter that considers the last n samples. And we found, I mean, where the output is the last n, x of n samples. And we are looking at the case where we are saying where it is the last 8 samples, for example. Yeah. And we are saying those 8 samples can simply be represented by y of 8 in the equation. Yeah. I hope you can all remember that we did yesterday. So usually there is more computation, more computation with FIR for the same selectivity, because remember the most important thing about filters is selectivity, being able to completely cut off the frequencies, attenuating completely the frequencies you don't want. Yeah. So these are the steps you have to determine specifications, and as we said again, the order, the minimum order is just actually some compromise. There is what you want, what do you want to achieve. what kind of selectivity do you want to achieve? Yeah. Do you want as closer to ideal as possible? As closer to ideal as you get, it would mean also your delay elements become more, there will be more computation. It means your processors have to be faster. It means your samplers have to be faster. Your ADCs generally have to work very fast, because as we said, you have to be able to do all the computations, and of course computations will depend on the number of delays and the number of multipliers. Remember, we are using the multipliers for scaling, the coefficients. So the higher the order, of course, means higher computation. So there will be you have to compromise. Yeah. So the transfer function of IFIR is normally in this form. This FIR, so it has no components. So then you select the realization structures. So there are, of course, there are very many. There are many of them, of course, which can give you the same result, the same transfer function. Yeah. But sometimes you choose the form. One is some forms will give you a saving in terms of the number of delay units you use, and we are going to see that. Yeah, I think there will be. I don't know that we have an example here. Yeah, so that would determine. That's why this stage is very important. Determining the filter structure, because depending on your filter structure you choose, you get certain advantages. Yeah, and I said one of the advantages, of course, if you have a structure that uses less filters, that's one. I mean, less delays. You can also have structures like cascade. Cascade is not mainly an issue of having less, but it's an issue of, instead of having a 4-order filter, you can cascade two 2-order filters. Yeah, so that will give you a cascade form. Yeah, cascade structure. Transposed, I actually transposed, I don't know what advantages it gives you, because transposed, I think instead of doing them here, I think maybe when we have a physical class, I can do them on the table. Yeah, can do these different types, but mainly we have direct from 1, from 2, and normally these forms happen in IIR. Yeah, 1 and 2. Cascade can happen in FIR. Transpose can happen in FIR. Lattice forms sometimes for where you have very many of very many, well, where you have a higher order, sometimes you may need, as I said, to employ structures that will give you less uh, less elements to use, whether it is multipliers. Normally, you can't do much about multipliers. Mainly, it is the delays. Oh, one advantage, for example, direct form are sensitive to quantization of the coefficients. Yeah, I think I tried to talk about quantization of coefficients. That is where your coefficients is a long coefficient, because of course if you work out the coefficients, and then they will have very long, it's a long number, the way they are stored in the computer, and sometimes you want to save storage by reducing the length of the coefficients. Yeah, you truncate them, and of course that truncation with the direct form, we won't work that out, but it can be shown that in direct form that that form is sensitive to that quantization. Cascade and parallel structures are less sensitive to quantization. We will get into those structures. Just know that. Implementation, you can implement in MATLAB as you are doing in your lab, I think. You can implement in Octave. Octave is a open source alternative to MATLAB. Yeah. C code, or you can do a hardware implementation such as a specialized DSP. We are good? We move on. So, to design FIR filters, we have very popular well-known methods. These are the window methods, and we have, I think this, as I said, since we are not in the typical DSP class, we try to minimize, because some of these techniques, they are complex. You need to have studied other things to do them. So we'll keep it simple. So we'll keep to the window method. Yeah. So there is a window method. We are going to see the window method. I mean, generally when we talk about the window method, what we are saying is the ideal filter. The filter that will give you the boxcar is h of n is supposed to be having infinite. It's supposed to be of infinite length. That is the ideal filter. I remember we talked about it before the break, when we talked about when we are looking at, what were we looking at? Let's remember what we were looking at. I think we were looking at intersample interference. Yes. And we say if you have in the time domain, if you have that boxcar, it means if you have boxcar in the frequency domain, it's in the time domain, you need to go from negative infinity to positive infinity. Yeah. But we are saying the rectangular in time domain gives you, in frequency domain, again negative infinity to infinity. Yeah. That is simply because how you move from negative infinity. I mean, how you move from time domain to frequency domain. Yeah, remember we use negative infinity to infinity, so it has to. You have to truncate. That's why we use a window. You have to truncate that HN, that ideal HN, that ideal impulse response. You have to truncate it so that it's realizable, so that you can have a reasonable number of filter elements. Yeah, not filter elements, sorry, delay elements, because that is one of the most critical part of a filter, the delay element. Yeah, and of course you're going to have fewer, less scaling multipliers. Yeah, so you have to do that, and how much you do depends on what you want to achieve. How many samples you use, how much you truncate depends on what you want to achieve. We can use the frequency sampling technique. It sounds like a very complex term, but what it actually means is, if you are given the frequency response, because that's what you'll be given, you want a filter with this frequency response. And that frequency response will actually be, you see you're dealing with the samples. So you're dealing with samples of the analog of the continuous time signal. So what you basically have is a DTFT. Yeah, is a DTFT. Yeah. So you can have DFT by frequency sampling the DTFT, and that will give you your HN in from the DFT. You do the IDFT. Yeah, and of course you can do optimal design, filter design methods. These ones just mean trial and error, where you pick coefficients and then you check the error and adjust your coefficients. Yeah, that's also a design method. So we are going to try to start looking at the window method, and we are going to look at just the general case. So in this method, the unit sample response HDN is determined from the desired frequency response, because normally you'll be given that desired frequency response. Yeah. So you're going to get the desired sample response HDN, that is impulse response. The desired impulse response, which will be given by this formula, that is 1/2 pi HD omega times e to the j omega n d omega. And of course, this goes from pi minus pi to pi. Yeah. The other important thing to note, well, not at this point, I think we are going to note it later. It's very important to understand, especially with filters, it's important to understand the relationship between omega and frequency. And then you find that filters, as normally specified, I think even, and I think even in MATLAB, well, not in MATLAB, but in some uh, filter design packages, is specified in normalized frequency. So you have the omega is equal to 2 pi f while I don't know, maybe I can call it the normalized omega is 2 pi f divided by fs, the sampling frequency. So it might be sometimes not intuitive if you are seeing an omega, because of course this is in, what is the unit of this? What is the unit of this omega? Candy? This frequency, yeah? What's the unit? So, Ocho, you said somewhere. You said the unit is? Okay, maybe when you're actually like this, it's not obvious, but of course, if you write it in this form, it becomes easier to see the units, isn't it?
Radians per second.
Yeah, it's radians per second. So that is radians per second, if you write it in this form. And of course, this normalized one, because you're divided by samples, becomes radians per sample. Yeah, per sample. That's sometimes can. So you may be given omega, this omega, or you may be given the actual cutoff frequency. So in your calculation, you have to convert to this omega. So whenever you're given that, you also be given the sampling frequency. Because remember, you're creating a filter for some analog signal. So we are creating a filter for voice, which goes to up to 4 kilohertz, then you're sampling at 8 kilohertz. So when you're building a filter, you have to be able to consider that. So in general, the unit sample response HDN obtained from the above relation is infinite in duration. Yeah, this is the thing. It's infinite in duration, and therefore it's not realizable. It's not practical. Not only, and it also goes from negative infinity to positive infinity, which means also your filter is not causal. Yeah, it's non-causal. It's not anti-causal, it's non-causal. So not only do you need, so if this is this, let's say it was like this. Oh. if it's going like this, let's make us, oh, no, this was the 0. Maybe this what you have symmetrical like that, from negative infinity to infinity. So first of all, you have to chop it, you have to remove this side and make it so it is viscoso. But now there's a problem because you want it to be symmetrical, so that it gives you a linear phase response. So what you normally do is first of all chop it, truncate it around 0, and then shift it so that it is still symmetrical and is coso, is both coso and symmetrical. Yeah, and I think we are going to see, maybe we are going to see it just now. Yeah. So in general, the sample response, yeah, it must be truncated at some point, say m minus 1, to yield an FIR filter of length m, 0 to m minus 1. So you are truncating at m minus 1. Yeah, so you have truncated, but once you truncate it, you have to move it to the right. You have to shift it so that it's also coso. So the truncation of HDN to this is same as multiplying HDN by the rectangular window. So we are going to see that we can use different windows, but we will start with a simple example of rectangular window. Yeah. There are 4 different windows which are used. I think we are going to see them later. So the rectangular window is Wn is equal to 1 for n from 0 to n minus 1, and it is 0 otherwise. So we have to see that. Other common windowing techniques include these windowing techniques. There's the Hanning window, Hamming window, Blackman window, and Ballet triangular window. I think I have got the formulas for this opposite Wn, which is just 1, and then of course I have for Hamming, and Blackman. I think I don't know whether they are here or there will be another document. There will be somewhere else. Later we are going to see them. So where were we? Yeah. So the other method is, of course, is frequency sampling technique. Yeah. So in this method, the frequency response is sampled to obtain a set of frequency. We are saying that because the frequency response is the DTFT. But that is why that's how you can see we are dealing. This is the DTFT. That's why you're using this formula. That's why we are saying, the DTFT of this sequence. These are discrete sequence. But the DTFT of a discrete sequence is a continuous function. This one. Yeah. So when you are, that's why when you are doing the inverse, you integrate. Yeah. So of course the DTFT is a summation, but the inverse is an integral. It's good to remember that the DTFT is a summation because you're dealing with a discrete sequence, but when you're trying to get your h of n from that, you actually do an integral. Yes, and I think I talked about this omega. So this omega, I didn't mention when I was talking about this omega. I've just remembered. Of course, this omega varies from negative pi to pi. It varies from negative pi to pi. So whatever you be given as omega will be between negative pi to pi. So it can be given a fraction of pi, or it can be given as a number. Yeah. So sometimes you're going to find you're being asked to design a filter which is pi by 4 with a cutoff frequency of pi by 4. Then you are wondering what that is. Of course, that will depend on what is the actual frequency. It will depend on the sampling frequency. Yeah. The actual cutoff frequency of that filter with that cutoff omega c will actually depend on what? On the sampling frequency. Yeah, so we are saying you can sample this HD omega, which is continuous at endpoints and create an endpoint DFT. And then by using IDFT, the filter coefficients can be calculated from the formula. And of course, sometimes why you want to do with DFT is for obvious reasons. Rebecca, why do you want to deal with DFT and not DTFT? Rebecca Rabera. Anybody who has an idea? We have done it before. Everything is connected. Whatever you do today is what we connected with what we learned the other day. Okay. Maybe I can answer myself. Of course, it's able to do fast DFT, which we call FFT. You're able to do fast Fourier transform. You're able to reduce your number of operations, yeah, when you deal with DFT. That's why sometimes you always go around trying to use DFT somewhere. So that's it. And then of course from that you can be able to get now your HN. Yeah. It will be easy to get HN from the DFT and HN because remember they are the same HN. So this you're getting from the DFT, now you're getting from IDFT. Yeah. And of course, the last method is which we will not look at is the optimal filter design method. The trial. The basic idea of this is to design the filter coefficient again and again until a particular error is minimized. An example of this method is the least square error design. Remember, we use this a lot in optimization, where you have so many possible inputs, and we're trying to look at the best combination of inputs to give you the optimal output. Yeah. Oh, you're calling an example, we have not done an example. Let us consider a low pass filter. That uh, filter, that frequency component from DC, some word is missing, uh, from DC to cutoff. That just means from 0 to some cutoff. A low pass filter normally goes from 0 to cutoff. Yeah. Sorry, just cutoff. I'm trying to look for the correct word, but we are saying a low pass filter that will pass frequency component uh, from DC to cutoff with no attenuation. Yeah, DC to cutoff frequency is a pass band. We call that the pass band. Frequency components in the stop band above will cut off will experience significant attenuation. Yeah. It means up to there, no attenuation. And then, so this is your signal, this is the amplitude of power. So, but after this frequency, this is a frequency against amplitude. And after here, our desire is that. So ordinarily you should have this as a pass band and that as the stop band. But the reality is that we are going to have that as the stop band, pass band, and this is a transition. Yeah. So the ideal filter should have a frequency response that's completely flat in the pass band and in the stop band. Completely flat in the pass band and completely flat in the pass band. However, a practical filter cannot completely flat, cannot be completely flat in the pass band nor in the stop band. Yeah, we know that doesn't happen. And why we are saying that is because we end up not getting the ideal H of n. Because the ideal H of n would have an infinite number of delay elements, an infinite number of multipliers. So it's not practical. Just 1 second, just 1 second. Let's proceed. So, and that is a practical filter. That will be a practical low-pass filter. Not only does it have transition, it also has some ripple in the pass band and also a ripple in the stop band. So what will happen, of course, it will depend on how you design your. If you have this Chebyshev, it will have a different characteristics. uh, from the others. We have many of those designs in the continuous filter design, continuous time filter design. I think I've already talked about this direct form generalization. I don't know why I put it here. Of the equation hz, this one for m is equal to 2 is shown in the figure. This is hz for m is equal to 2, where you have only 2 delay elements. So the order of the filter is 2 and the coefficients are 3. So if the order is m, the number of coefficients is m plus 1. Yeah, I think that's what I said here. So lambda of the filter has m plus 1 coefficients. So bk is the value of the impulse response at the kth instant of the m order filter. Yeah. For direct formal fire, bk is the coefficient of the filter. Yeah. For direct, this is the coefficient of the filter. Yeah. This computation. Oh, we are saying actually this is simply discrete convolution. Yeah. Linear phase response is very important, having linear phase response, because the moment you don't have linear phase response, that is, the frequencies are not affected equally. Yeah. Then you end up having distortion in the passband. Yeah. So to get that, there must be symmetry in the time domain. That is, Bn is equal to plus or minus Bm minus n. Yeah. I think, I don't know whether we haven't done it here. But what it means, Bn, let's see. Let's check the case where m is equal to 5. To understand this, so this is Bn is equal to Bm minus n. So this is B0. M in this case is 5. Oh, of course we have already B4. So what we are saying is B1, this one, is the same as, okay, we are considering Bn to be where? Trying to see whether is the same as B5, B4. We are counting from here, sorry. We are counting from here. So this is B0. Yeah, this is what we are counting from. Oh, symmetry. I was trying to, traditionally we consider B0 to be the center here. But if we are considering B0 to be the first one, so B0 is the same as B0 is the same as B5. So this is it, same as B5. Yeah, 5 minus 0. It's the same as B4, sorry. Because this is B0, B1, you know, traditionally we, of course, we start with 0, B3, B4. So M in this case so B0 is the same as M minus N, which is M minus 0. Oh, in this case, m is 4, sorry. Oh, if of course, if there are 5 coefficients, what about that? If there are 5 coefficients, it means m is equal to 4. That's where I was having a problem. Yeah. If there are 5 coefficients, it means m is equal to 4. So B0 is the same as B4, is 4 minus 0. B1 is equal to B3, 4 minus 1. And B2 is simply itself. It's the same as B2. Yeah. Yeah, so good to remember that if you have 5 coefficients, m is equal to the order of the filter is 4. Yeah. So it means that the second order realization shown above, in this shown above, B0 here, B0 is equal to B2. In the case of this one, where m is equal to 2, B0 is equal to B2. Yeah, it agrees with our formula here. Yeah, please know that linear phase response proportional, that means proportional to frequency, corresponds to a constant delay. It means different frequency components of the input will experience the same time delay as they pass through the system. Yeah, you don't want their phase to change. Yeah. So filter, we'll do a general example of a filter. I'm calling it general because in this case we are not giving the value of omega c, the cutoff. We're just looking at omega c. You want omega c, whatever the omega c is. So let's consider a low-pass filter with the desired cutoff frequency of omega c. The desired frequency response, we use the HD to mean the desired. So that from there we can be able to get the small HD n, which is the impulse response, the desired impulse response. Yeah. So in this case, we are given the HD omega as 1 for omega is less than omega c. When we use absolute, it means it goes both to negative and positive. Yeah. So actually, what we are talking about is a filter which looks like this. Yeah. Minus omega c, omega c. So from up to pi, or this is minus pi to pi. So it does not, of course, elsewhere means from minus pi to minus omega c and omega c, because this only varies from negative pi to pi. Yeah. So we are talking about this. This is the pass band. I mean, this is the stop band, and this is the pass band. Yeah. So 0 elsewhere. Yeah. So you have that. So you have the inverse discrete time for the transform. Of course, if you do inverse discrete time for the transform, you're going to get HD of n. Yeah. Because this is the discrete time for the transform. So if you do is inverse, you're going to get the H desired n. To find the equivalent time domain representation, find the inverse of this dTFT. So HD of n is the inverse of dTFT of HDW, H sub d omega. So HD n will be 1 over 2 pi, negative pi to pi, HD omega, EJ omega, ND omega. substituting equation 1 into equation 2, which means all you're doing is, you have been told it is 1. So this is simply 1 times that. So this is HD from here. Oh, where is my... Ah, yeah. This is 1. So you simply get that. Yeah. Because you have been told the response is 1. So this works out to this. Sine n omega c over n pi. The impulse response for omega c is pi. Oh, it's shown in figure 3. Let's see. Oh, what is the figure 3? Ah, of course, I've not shown the value, so yeah, it doesn't matter. I'm saying this is specifically for pi by 4. But since I've not given this anything, so but it should look like this. Generally, it will be of this form. So I'm saying for this particular one, it is this. I should have given some numbers here. As I said, normally omega c will be given something between 0 and pi. Yeah, because in this equation, in this omega c, we use the normalized angular frequency. So this is normalized angular frequency. It's not the 2 pi f. It's 2 pi f over the sampling frequency. So that is what we have for the case. WC is pi over 4. It will look like that. Generally, it will look like that. Whatever it is, it will normally be. Why did we choose pi by 4? Let me see. Oh. Pi, I'm doing this one, pi by 4. Generally, it will be this shape, whatever the value of this is. Yeah, it will be how this. It will be a sink. It will be some form of a sink waveform. Yeah, I think it's called that. Yeah. We are good. We had booked this lesson for 3 hours. So I was trying to think, do we do 2.5 hours? Is that agreeable? Or do we just do a normal 2 hours? Hoping the semester will be extended. We try to be extended, we don't know. We don't have any Sherry, where? What's your opinion?
Yeah, depending on the content for today, you can.
Oh, depending on the content, okay. Because the content is a lot. But okay, let's see how far we can get. Yeah. No, just hearing that the content is heavy. We are doing so many different things, and sometimes it reaches students reach saturation. So you have talked about it, but at some point, you become saturated. Let's hope we will get there. So let's continue. I hope we are moving together. Yeah. So this will be the desired for this WC 5/4, but this is not realizable because this is supposed to be going from negative infinity to infinity. It is also not causal, just this part. Yeah. So figure 3, it is seen that it requires an infinite number of input samples to perform filtering. Basically, that's what it means. When you have a very, very long HM, it means you require all those sequence samples before you can do the filtering. Yeah. The system is also not causal. Yeah. So this filter is not realizable. To make it realizable, HDN has to be truncated. And we see that truncation of the impulse response is done by multiplying HDN by a rectangular window WN equal to 1 over the window. As the number of samples increases, the truncated impulse response will be closer to the ideal response. As you increase the number of samples, increased number of samples means increased hardware requirements. Yeah, that's so it is kind of an optimization. Yeah, it's not really optimization; it's just a compromise. It's kind of there's a word I'm trying to look for the word which the politically correct word in engineering. It's not called compromise. It's called some of these words disappear in class. Yeah. Huh? Yes, somewhere. Look, you're giving me that word.
Could it be trade-off?
Oh, trade-off. Okay, trade-off is a word. There's still another word, but it's basically a trade-off. Yeah, that's a good word. But trade-off is there's still another word in engineering, which means the same thing, which means trade-off. Yeah, but trade-off is a good one. Yeah. So impulse response of an ideal, we are still continuing the same thing. Figure 4 shows truncated, non-causal, non-linear phase impulse response. So I think what we have done here, we have truncated to 21 samples, negative 10 to 10. So these are 21 samples because of this zeroth sample. Yeah. So this will give us linear, huh? But non-causal. Huh? Figure 4. Where is 4? Yeah. This 4 is non-causal, but is truncated. Yeah. So, there's something. This is causal, but non-linear. Oh yeah, that's it. Oh, this is causal and linear. Causal, but non-linear. This is causal and non-linear. Non-causal and non-linear. So it's non-linear phase. Although of course this is the actually this should have been linear because it is already in this. Actually, this should be causal, non-causal, but linear. You know, because it has got this symmetry. Yeah, it's non-causal, but linear. Yeah, this is causal, but non-linear, and this is causal and linear. Yeah. This is non-causal linear phase. It is linear phase. It's already in that format. Yeah, it's non-causal but linear. Yeah, so this one is causal but non-linear. But we can make it by, instead of, we truncate it first to that, which is going to make it realizable. But this in its form is already around here is around here it is actually symmetrical, so it will give a linear face because of this symmetry. Yeah, but it's not realizable because it is not causal. So probably that's why we are saying, well, I think that's why you are saying it's nonlinear, because of this. It has to be truncated, but it's also realizable. So ideally, it's not realizable, although it could give us linear face just from the shape. It's not realizable because it's non-causal. But so we can, instead of truncating to make it causal, what we do, I mean, instead of truncating, removing this half to make it causal, what you can do is what? Is shift everything to the right. Truncate and shift to the right. That gives us the two requirements: causal and linear phase. So frequency response of the filter designed by a rectangular window. So we said, of course, this window is a rectangular window, because what we are saying, we are multiplying this HDN by a rectangular window. So that's for truncating. Yeah. The HDN is this one, rectangular window, where this is the window of the triangle of the rectangle, will simply give us that. Then we do shifting. So we have the symmetry, and then we have causal. So so figure 7, which is figure 7, yeah, this figure 7, this is the ideal filter and this is the design filter, and that's okay. This is the spectrum of the rectangular window, the window we are going to use. Remember, we have a rectangular window, omega n. Now this, we're going to have a rectangle in one domain, but it gives you the sink in the other domain. So if you have a rectangle in the time domain, to give us the sink in the spectrum, in the frequency domain. That's why you can see the frequency response is of this form. So although, what does it mean? Although we are in the time domain, we are doing this, there's an effect on the frequency domain. That would be the spectrum. Yeah? There's an effect on the frequency domain. So it will affect the frequencies. Yeah? And this main lobe and peak side and the peak side lobe affect the output. Yeah? That's why actually that's why sometimes we don't use the rectangular window. You try to use windows that will compensate some of these effects. These other windows, the Hanning window, the Hamming window, they would give us a better side lobe and a better main lobe. We are going to say that. And actually the explanation is here. The design filter has a smoother transition from the pass band to the stop band. ripples are present in the passband as well as the stopband. Yeah. I think most of the information is in the next document. So it's so far so good. Nobody has issues with what we have done so far. You have picked a few new concepts, I hope, and some of them actually applying concepts which you have learned earlier. Yeah. So we are good. So let's proceed to this. I started again with the window even shifting. So a due frequency response has infinite impulse response. I've said it so many times, very important. It means that the FR requires infinite inputs to be implemented in particular to be truncated to make its constants be shifted to the right. Truncation is just multiplication by triangle in the function, yeah? Yeah, so, I've gone back. So, effects of rectangular window on the desired frequency response. You see? So, when you use a rectangular window, of course, it also affects the frequency response. You have multiplied the HD, but now the HW, or the product of the two, it is going to affect the output. The greater the areas that have the side lobes, the larger the ripples in the sideband. Yeah. The width of the transition increases with the width of the main lobe. Yeah. The width of the transition depends on this. Yeah. M should be as small as possible in order to have few computations. And we are going to see this M. You can see this M is important here. Yeah. That is the order. We are saying, of course, in future design, you try to use the lowest M, the lowest order that will give you the desired result. Yeah. To reduce the computations, to reduce basically that's what happens in communication. I mean, you want to maximize how much data you transmit in a channel, or you want less to use less or more. The same thing here, we want to filter but also reduce computation, because computations mean time delays, and delays will end up having an effect on what you are trying to communicate. So this, of course, when you say this is the when you talk of W, actually this should be, I think it's because I was having a problem of writing omega. Rather, I was lazy, I was not going for, I can write it. This is omega and this is W omega. This means the spectrum of the window. So this spectrum of the window should be as close as possible so that HW is as close as possible. So you can see what we are saying. This transition is determined by the size of this loop. So it should go as close as possible to a Dirac delta, yeah. So it should be like this. That's what we are saying. It should go as close as possible. If it becomes a Dirac delta, there will be no, then H desired will be the same as H omega. Yeah, you get it. That's what you're trying to say. This should be as close as possible to the Dirac delta. For this to be as close as possible to reach the omega, the width of the minimum bulb decreases as m increases. You see, the width decreases as m increases, and of course it makes sense. It is actually intuitive because the width of the main lobe determines this slope. Oh, why is that slope? This slope. And we are saying this slope decreases as the order of the filter increases. So this is very, you can say it's very intuitive, yeah? The width of the main lobe decreases as m increases, yeah? Because a decreased main lobe means this is closer to the ideal, which means you're getting a very sharp cutoff, yeah? So that's the frequency response of a particle low pass filter. I think I've done it before. Effects of that, the filter of a large order has a narrow transition band. We have said that so many times. However, sharp discontinuity results in side lobe interference, independent of the first order. I think to understand this one, we need to do a proper analysis of this very common gift phenomenon. That narrow transition band, that sharp discontinuity, as good as it is, it has its own effects. Yeah. Windows with no applet can be used to reduce this. So we can use windows with no abrupt discontinuities to reduce gift oscillations. This includes Hamming, and Blackman. And I think we have here. Oh, we have not given the equations. I've not given the relationship. I've only mentioned this one. This is a formula for the Hamming window. Yeah. I think I should. That's a formula for Hamming. That's Hamming, yeah. That's Hamming. Hamming is a bit different. Yeah. So in our case, it's Hamming. Is a case for the Hamming. I think the Hamming window is Wn is equal to 0.50 minus 0.50 cos 2 pi 2n pi over m. Yeah, the same, but just these coefficients are different. That is a Hamming. Yeah. But anyway, I think I'll try to maybe give you the correct figures. I mean, they are everywhere. They're over the internet. You can get those Hamming, those windows, different windows. They are Wn for rectangle, of course. Wn is equal to 1 for that, and then 0 otherwise. Yeah. And for Hamming window is this is equal to this, not 1. For n is equal to 0 to minus m and 0 otherwise. Yeah. Yeah. Where were we? We were here. Yeah. So the steps from the desired specification. So we will select suitable window function. So we have already got HD, H desired N. Yeah. So compute uh, yeah, suitable window function, compute the coefficients of the ideal HDN. I don't know whether this should be the ideal. You're not actually. This is the desired. Actually, we normally call it HN. Actually, we don't do the coefficients of this. We do the coefficients of HN. But anyway, we are going to calculate the coefficients of HN because you have already subjected this HDN, the desired. Actually, not the ideal. That should be the desired filter to a window. And when we do that, we call it just HN. Another HN multiplied by the window. We call it HDN multiplied by the window. We call it the HN. Multiply the ideal coefficients of by the window function to give filter coefficients. Yeah. Okay. I think it's the same thing, but I don't know whether you want to do the coefficients of the ideal filter because they'll be infinite. So normally you don't do that. Ideally, that's what you should do. Compute the coefficients of the ideal filter, and then subject that to the window function. But we normally don't do that. We normally subject this to the window function, and then calculate the coefficients. Yeah. Evaluate the frequency response of the resulting filter and iterate it if necessary. That is, increase n if the requirements are not met. And then, of course, from that Hn, you can be able to get your H omega, capital H omega, which is your impulse response, or Hz, and then check whether it does what you want to do. If not, start again. Iterate, just keep on doing it until you get what you're looking for. So these are the different windows. Yeah. So I did not give the formulas of the windows, but what is important, especially in the design, is this information: approximate width of main lobe. So depending on the width you want, yeah, do you want the width, like, I think in our case here, which we are going to look at in the next class, we were looking for a width of, I should not have written this one here, a width of what was the width? Transition width is 0.2 pi. So this divided by this, this must be equal to this is 0.2 pi. Sorry. I was saying this. So we are calculating now m from the width we want. Are you getting me? If you are going to use Hamming window, for example, then it means the width will be equal to this. So depending on the width you want, you determine the m. Yeah. Very important too. That's why this is very important. Again, the attenuation will depend peak side lobe amplitude. because that will determine the attenuation. This one determine the attenuation, yeah, a stop band and at the one of them causes one of them affects the ripple. I think maybe we can do that tomorrow when we are doing, I mean in the next lesson when we are looking at this using Hamming window, yeah, so that you don't get confused. We can look at that tomorrow. So today we're just going to do this example, a filter design using the rectangular window. So FIR, this is now an example where you're given the HD omega. You have been asked design a low pass filter with the desired frequency response. So you're given HD omega. E is equal to minus m minus 1 to omega, or omega is less than omega c. This is an interesting example because normally HD omega is of this form. It's normally of this form where m is the order. Yeah, the response will be of this form where m is the order. Yeah, but here we have given the case whereby it is normally whatever this, okay, some books will call it tau, and it will be j tau omega or j omega tau e to the minus j omega tau, where tau is m minus 1 over 2. So deliberately in this example we chose m minus 1 over 2 to be here. Yeah. Anyway, you see how our choice works out, because normally the response will normally be of this type, e to the minus j omega tau, where tau is equal to m minus 1 over 2. Yeah. So we have just used that m minus 1 over 2. So from the desired frequency response, the desired impulse response can be computed by IDFT. So our HDN is 1 over 2 pi, from pi to minus pi to pi, HD omega e to the j omega n d omega, which gives us that. We have put this one here, which what we have done here, we have let, we don't want to keep on working with m minus 1 over 2, so we are working with a, which will have been our tau here. So we are working with a, so we are saying 1 over 2 pi omega c, because now here our limits we have been given as omega c. So our limits now does not go from negative pi to pi, it goes from minus omega c to plus omega c, e to the j a omega, e to the j omega n d omega. So this is simply, you can add this simply becomes 1 over 2 pi minus omega c to omega c e to the j n minus a omega d omega, which becomes, you can reorganize. Actually, you don't have to reorganize this. Of course, once you integrate this simply becomes e to the j n minus a omega over, yeah, that is of course any, I think it is any, if you have e to the ix dx, it will simply become E over Ix over I. Yeah? I don't know what it means. Yeah? Whatever was here comes here. Yeah? Oh, I in this let me just use Ax. We associate I mainly with the, yeah. I think that's what it becomes. If you integrate this, you get this. That is this. So, um, so you have this, and from minus omega c, you evaluate it for these limits, and what does it give us? It gives us 1 over 2 pi e to the, yeah, of course, when you use omega c and minus omega c, this is what you get. And actually, this is very important when it comes to filter design. This I'm looking for the correct word. Let me go this. These words keep on me. Identity. These are trigonometric identity. These are identity. It's trigonometric identity. Sin of x is e to the power of ix minus e to the minus ix over 2I. Yeah? So whenever you have this, you can simply call it sin x. Yeah? So, and you can see this is of this form if you remove what? If you remove, oh, 2I. Why am I not getting I? Ah, sorry. There's this J. I was wondering where I'm going to get the I. Our case is the J. So we have the J. So what we are going to do is just reorganize this so that you get 2J here and you bring this here. So it becomes pi into n minus a, and this has 2J here, and therefore, actually that's what we have done. We have reorganized this. So this becomes sin n minus a omega c. Yeah. So whenever you are faced with this, always try to use this identity so that you can move from the exponentials, you go to the sinusoids. Yeah. So you get this 1 over n minus a pi sin n minus a omega c. Yeah. And of course, this is familiar. You can see this should be, no, it's not exactly as assumed. So that's what we have. That's what we get. And now Hn, of course, what you are getting, what you have gotten here is what? Is Hd omega. But we want, is Hd, sorry, is Hdn, the desired impulse response. But now we have subject that to the window. So we accept this, we multiply that with the window, and our window is that 1 from 0 to n, n is equal to 0 to n minus 1, and 0 elsewhere. So h of n is simply that. So we're just multiplying by 1. Actually, it doesn't change. It remains the same thing for 0 to n minus 1. So it only means our hn only moves from 0 to n minus 1. Yeah. So h of n, of course, we can put back our a, which was n minus 1 over 2. So we get that in this case, let's look at where m is equal to 5, where you have only 6 coefficients because the order is 5. Yeah. And of course, when you have m is equal to 5, oh, you have 6 coefficients, you have 4 coefficients. The coefficient should be more. Let's see. Oh, 5 here seems to be the number of coefficients and not the order. Okay, so we have that. If we replace m is equal to 5, of course, we are going to end up with this. So our HN will be this from 0 to m minus 1. Yeah, so that will be 0 to m minus 1, m minus m is 5, so m minus 1 is 4. So it will be 0 to 4. So now we can work out the DTFT. Actually, what we have done here, we have not even calculated. It depends on what was your question. Our question here was to get the frequency response. But if you are just being asked to get your HN sequence, of course, what you have done, you just have replaced this from 0 to 4. Yeah? You just have replaced this from 0 to 4. But in this case, I think we have been asked for the frequency response. So you have to try to get. So please note, it depends on what your question is asking you. What is the question? It's always very important if it's an exam situation, you read what is asked for. Because ordinarily, if you do an example and you reach up to here, you think you have gotten it and you give this. But here you ask for the frequency response, so we have to get our DTFT. So our DTFT is this H omega to the omega. We can call it H to the omega, H to the J omega, H to the J omega is negative infinity. This is a summation of infinity to infinity. H of n e to the minus j omega n. Always remember the inverse as j omega n, but the DTFT has minus j omega n. So h of omega is equal to this. The summation is, of course, now we know the summation is from n is equal to 0 to n minus 1. Sine of into bracket n minus 2 over n minus 2 pi times e to the j omega n, this one here, times this. And if you replace this, this comes to this. So the first term is this one. This is for n is equal to 0. So it becomes that. N is equal to 1. N is equal to 2. I wrote it like this. But normally, of course, this sign 0 by 0 is indeterminate. So here we normally use what I think it is called this sign x. If you do the limit of sign x over x as x tends to 0 becomes 1. I think it's called the L'Hôpital's. I find people calling it the hospital, but it's, I think, Le Hôpital. Le Hôpital. Hôpital rule. I don't know if they have done it in maths. So there is this rule is one that tells us when as this tends to get 1. Of course, that is one way of doing it. The other one is simply working it from h of omega. If you opted from h of omega, it will still give you just 1 over pi. Yeah. So like this becomes just 1 over pi. Yeah. You can either work it from this, so it becomes 1 because this will become 1. Yeah. Because of 0. Why am I? Oh, e to the 2j omega. So this will become, oh, it will be this. Ah, no. This one will be this. It will not be 1. It is this that will become 1 because of the limit. But we never write it in this format, right? Just look like this. Never write it in this format. We normally do that limit, and then this becomes 1 over pi times e to the minus j 2 omega. You could have done this through the through this, where if you get where am I? Yeah, you can apply the L'Hopital. I think that's okay. L'Hopital. So this will be, so that will be the first, so this will be the frequency response, which has got these 5 terms. So this is for n is equal to 2, n is equal to 3, and n is equal to 4. Any question with this example? And most examples, I mean, most solutions will actually go through these steps. But it also depends on what is asked for. Otherwise, it would have stopped here. If you have been asked for the impulse response of the filter, it would have stopped here. If you ask for the frequency response, then you go up to here. The only thing that varies is the cutoff, what you're given as HD omega, because sometimes you could be given a value, like you said, HD omega is 1, but then the order is specified separately, M is specified separately. Yeah? So that it's important to know that. Or you may not be given this as this omega, the normalized frequency. You may be given, like we have done here in this format. You can see, design a low pass filter with f-stop 240 Hz and f plus 360 Hz. So in this case, you are not given omega. Here you are given the frequency. But whenever you are given the frequency, because in this equation you have to use omega, normalized omega, whenever you use the frequency, you have to be given also the sampling frequency to be able to calculate your omega. And that's what we are going to do next, in the next lesson on Wednesday, because we have agreed, or I hope we agreed with that one, because you had proposed the cut on Thursday, and I said, I don't know whether you want to do the cut on Thursday at 4 or you want to do the cut on Thursday at 8. Because the hours in between will be tied up. So yes, Rufin.
I think Thursday at 8 will be okay.
Thursday at 8 will be okay. Very good.
Yes.
So we have Thursday at 8 is a cut. So Wednesday is when we are going to do this example. I think I don't know. Well, I think we can have do we do physical or do we do online? This one class on Wednesday. Okay. Sherry, no, not Sherry. Is Serfin. You inform me what you have agreed,
Yes.
and if it will be raining. Yes, Samuel, you have put your hand up.
Yes,
Yes, Samuel. I think some filter is not working.
I
Filter
have
of your
spoke.
face.
Oh,
Yeah.
I hope it's okay now.
It's okay now. I can hear you. It's still distorting.
Yes,
Just
so
yeah,
past years for potential examinable areas,
yeah,
I came across 2D convolution where we have the smoothing, edge detection, kernels, etc. And I
yeah.
realized we haven't covered that, nor
Mm.
do we have the notes on that in the classroom. So I was concerned and I was inquiring if it's an area we'll cover and if we should expect it in next week's cut. Areas on 2D convolution.
No, it won't be the next cut. In fact, that is fully in the syllabus. Is we are going to cover that after we cover this. Yeah, actually, when we started covering these filters, is because what is in the syllabus is the 2D convolution filters, and I thought you can't begin talking about 2D convolution filters when you have not even done digital filters. You have not done digital filtering. That's why I included this. This was it's not even in the syllabus. If you look at the course content, it doesn't even include this. Yeah, but I discovered actually it's required because you are doing the lab in it. Initially, I've been made to understand that you don't do DSP. DSP is done for masters and not. That's what I have been made to understand, and that's why any topic in DSP which is not in the syllabus, I didn't cover it, and I only covered this because I thought it's wise that you understand digital filtering before you go to 2D filtering. So we are going to do 2D filtering, but it's not going to come in this cut because we haven't looked at it. Actually, it will be the next topic after this digital filtering topic. Yeah, that okay?
Yes, that's okay.
Okay, very good. So you people have a good day, good weekend, and we see you next Wednesday. Thank you very much. Oh, and kindly, as usual, your post your registration on the chat. Thank you.